Okay, good morning, everybody, again. We're starting our energy and transport panel. I think this is one of the most advanced areas that the collaboration between government ministries, IIASA and academics is happening at the moment. And we really appreciate it, and we think it's really important. And you will hear today first, Dr. Paul Kishimoto from IIASA, which is representing the ECE department, the Energy, Climate and Environment program within IIASA, about their program and what they're doing, and also specifically about the model that they developed there. And then we will move to hear about the Israeli baby of that model by Ayelet and by Shahar, and we will see the academic part and policy. I will use this model in policy. And then we have really great speakers to share with us other work that is being done, and I will introduce them as they come along. Work that is being done in different institutions here in Israel, all related to energy system, to net zero 2050, to the economic side, to technology, and to transportation, all using very advanced tools and methods. And I think it will be really great if we could think, after we finish that session of presentation, how we can integrate this type of work. And again, this is just tip of the iceberg. There are a lot of other researchers, and again, it's just the beginning of stirring up kind of thoughts and bringing in more scientists from our institutions to be involved in that. So without further ado, the floor is yours.
Thank you so much.
We will just to 10:15. We will try to have at least half an hour for discussion at the end. And I will try to time you in on the presentations, but
okay, great.
If I want to send, what is the link for this?
So if you go to the easiest now is to go to the IIASA website, the main website, and the events, you will have all the links there for each panel. So this is just the easiest at the moment.
Yeah.
So it's a Zoom webinar. They can just join. Okay.
Thank you so much, Farad. It's a really delight. It's a delight and a pleasure to be here. As Farad mentioned, my name is Paul Kishimoto. I'm a research scholar in the Energy, Climate and Environment program. So I'm actually more at foot soldier level. I'm not the program director. I'm not a group leader. But I'll give you a little bit about the structure of our program and the things that we're involved in. And a lot of what I'm going to show you today is work that's done by my colleagues. So the EC program in total is close to 70 people at this point. We have 4 research groups within that. The team that's working on or applying this MESSAGEix global biome framework, I would say, is on the order of 25 people. So more likely the things that I'm going to show you are things that my colleagues have done in parallel to my own work. As Farad mentioned, my focus is on transport, so I do lead a number of projects that we do on transport and mobility within this framework or related to it. I'm actually not going to spend a lot of time in this presentation talking about that. I really want to give you the overall picture, and then we can zoom into either transport or other energy or related topics as your questions and interests dictate. So this is very similar to what Albert presented about IIASA as a whole. So you'll see, themes reflected, but slightly more specific for the different programs. So the context, the challenge that we are motivated by is this idea of multiple crises or multiple environmental challenges that have a variety of social impacts and negative impacts on well-being. And in particular, we're motivated by the physical boundaries of the planet, right? The ecosystem carrying capacity of the planet that we're on. And those are long-term physical boundaries, but we have short-term policy objectives and human systems that are pushing us towards, and in some cases are past those boundaries. Many of those problems are global in nature, but they have aspects that are regional, national, or local. So for instance, the water is an issue that is global, but the manifestation of the water issue is very different in different places. Right? So what we try to do to address these issues is we're interested in, first of all, just scientific knowledge and understanding, right? Understanding the nature and dynamics of these systems, and then how those systems might be transformed feasibly to address those environmental problems in a economically and equity standpoint sustainable manner, right? And through that work, out of that understanding, we would like to provide policy support, systems analysis that help decision makers manage these trade-offs that exist or exploit synergies, and especially when those problems and decisions that they involve are crossing scales, both spatially and temporally. And then finally, that really leads us to, hopefully, ideally, I don't think we're quite there yet, but what we'd like to do is provide support for local policy decisions, things that are needed to do in the short term, but at the same way have confidence that the sum of those decisions across many localities, many countries, and many systems is going to add up to a overall transformation of the human Earth system that is going to keep us within those boundaries and be sustainable in the long term. So what this is, again, you heard it from Albert, you heard it from Barrett again. I'd just like to reiterate this point. We'd really like to hear from all of you in the discussion part. Do any of these research questions and topics align with the existing foci that you already have? In what areas can the modeling capabilities that we talk about complement or help meet the needs that you know of for research to provide policy advice in Israel? And in the converse, what areas do you have expertise where you can help us sharpen the picture, right? So because we start from this global long-term perspective, our ability, our bandwidth to zoom into particular countries, particular phenomena that are maybe occurring in very important in certain places, but not occurring everywhere is very limited, actually. So we really rely on people who have close knowledge and expertise in particular sectors and subsectors, or in particular countries, to help us understand what and how we can do better in terms of capturing the integrated picture of the whole global system, right? So that can be methods that feed into our global models or that are fed from the global models, or they can be a better representation of the current state of the energy system and real policy, be that through just sort of qualitative vetting criteria through data that you have or anything of that nature. Okay? So I'd love to hear a lot about that. Again, please don't try to digest the whole diagram. Just to say that we have what's called an integrated assessment model framework. The name is MESSAGEix Globium, and it's a modular adaptable family. All these words have meanings. I'll try to walk you through it. To say that in the inter and transdisciplinary sense that we are integrating not just an economic perspective, not just a engineering systems perspective, and not just a physical science perspective, but trying to link all of these things together in a framework. At the same time, we don't want it to be glued together into a solid mass. We want it to be modular so that we're not sort of obliged to operate this huge unwieldy machine for any research question, but rather we can pick and choose and use the parts that are germane to a particular research question. So, and we use them for assessment, that's assessment. And we say family because all of these models that we build within this framework have a largely similar structure, but they can be adapted and tailored somewhat to the applications and the research questions. So the centerpiece of it is this linear program systems engineering model called MESSAGEix that has been through several generations over the past decades. And then it gets connected to, for instance, the macro model for macroeconomic feedbacks. We have some sector-specific models, buildings, materials, and transport. And I'm showing you in dark the ones that are used or have been used, I guess, thus far in our Israel collaborations. The others are used more with the global applications of this model framework. So starting from that global model or the global model family, one very common thing that we do in a lot of research projects is we break out a national model, right? So we start from different versions of the global model, which does provide some flexibility for different use cases. And when we segment out a national model out of the global model, that provides some practical advantages in that we can use the same tools, calibration, reporting, post-processing, all of those. And we don't have to reinvent those wheels, for a particular application. It also provides the possibility of soft or hard linking a national model with the global model so that global energy system dynamics can be captured in the global model and then fed into or provided as exogenous conditions to a national model. And there's a variety of, I'll show you some examples where this has been done. Another thing that ECE does is, especially at the initiative of our director, Kevon Riahi, is we play a very central role in global scenarios processes, right? So MESSAGEix Globium is not the only integrated assessment model or model framework out there. There are many others developed by other research institutions, and it's very valuable to run similar scenarios through them all and then compare those to see slightly different views, right? This epistemic uncertainty about what actually is happening in the system and what pathways to transformation might be. So one of the most noticeable manifestations of that is the IPCC assessment report working group 3, where a variety of scenarios were collected on database infrastructure that we set up and maintain in the ECE program. And we use those to look at some of these topics, right? So a variety of different pathways or strategies for reaching net zero, the role of the agriculture, forestry, and land use in reaching those net zero targets, the degree of investments or changes in investments in different areas of the energy system that are needed to provide those pathways, and also on the impact side, what are the benefits of mitigation. As a consequence of this, we're very heavily represented in the AR6 authorship. So I was a contributing author on the transport chapter in working group 3, but we also have CLAs, LAs, summary for policymaker authors. We have author on the synthesis report. And so, very much enmeshed in that process. Another capability that I should mention is this GAINS mentioned in the bottom there, which is developed by our pollution management research group. And this is a model that connects not just greenhouse gases that are related to climate change, but also local air pollutants of all types. And it's very highly resolved, a lot of detail about different technologies and mitigation options for local air pollutants. So this is just showing some example results where that was applied to help the EU Commission set some ambient air quality directives and try to think about how improving air quality and the other policy targets to decarbonize Europe in general can be done at the same time, how those efforts align, right? So now I'll go into some examples of national projects. Again, I'm not going to go into the detailed structure, methods and results of each one, but just to mention, to give you a flavor. And if you're interested in particular ones of these, there's a lot of detail on the IIASA website, or you can contact me and I'll put you in touch with the colleagues who actually did this work. I'm just showing it off for you. So one example is with University of Federal de Rio de Janeiro. So we worked on looking how the Amazon and carbon sinks in the Amazon can help meet the country's NDC pledges. With the government of India, so NITI Aayog is the major planning agency of the Indian government, looking at water, energy, land modeling tools, and I think might come back to that in a sec. With Egypt, there was a study looking at the trade-off between the export of green hydrogen versus natural gas to Europe. And with the Green Climate Fund, they have a country program. So we've been funded in 2 cases to work on country-specific mitigation pathways for Lebanon and Uzbekistan. So just to explain a little bit more why that's needed, a lot of the global pathways that show up in the IPCC, these are representing the whole world at the level of aggregate regions. So how does North America decarbonize? How does Europe? How does Sub-Saharan Africa? And that's useful for the global picture. But when it comes to policy relevance and decision-making, of course, Lebanon doesn't want to do what all of Middle East and Africa is going to do. So they need a more specific, tailored picture. So my colleagues who worked on the Lebanon case, they were analyzing the economic and environmental implications of their updated 2030 nationally determined contribution under the FCCC. And one of the things they found that was quite interesting there is there's a very large potential for substituting out these small scale diesel generators, which are very prevalent in that country's energy system, for renewable electricity. However, the amount of investment in renewables that is written into the NDC is really not consistent with Lebanon playing its part in a global trajectory towards achieving 2 degrees Celsius mitigation. So what you're seeing in the two plots on the left is what's in their NDC, and on the right, what would be needed for a 2-degree target. And these are several different areas of the energy system and how the investment is greater or less in those particular policy cases versus a baseline case, right? So you can see in both cases, investment into fossil fuel extraction and use has to be scaled down, but in the NDC, it's not scaled down enough. And in both cases, investment in renewables and energy efficiency should increase, but in order to meet the 2-degree target, those increases would have to be a lot larger than is actually written into the NDC. This is the example of the sort of policy relevance conclusions that come out of the modeling work in these projects. So very similar for Uzbekistan. Again, this is a focus on investment. On the right side, there's a variety of different possible emissions trajectories, and the country can think about which one they want to be on. And on the left side, just showing that the investment picture for 2 degrees versus what's in their 2030 energy policy is quite different. So I guess an important point is that Lebanon and Uzbekistan are very different from one another, right? So there are extant policy discussions and so on, and that's why this sort of stakeholder engagement to understand what do we need to model, and then how do the quantitative results out of the model have to be framed and interpreted to be relevant and useful in those policymaking processes. The last national example is from South Africa. So South Africa's NDC. I'm laughing because I lived in the US during the whole shale gas boom, and it's now very much out of fashion, right? As some of you might be aware. So, but South Africa is still relying on shale gas as a major mechanism to meet their NDC targets, and so there is a notion that gas can function as a transition fuel, moving from coal to renewables. And this was actually a visiting PhD student. Really emphasized that the major question mark there is methane emissions. So the US is still not doing a great job controlling methane emissions. If South Africa does not manage the methane emissions, then the climate effects of that gas usage can be quite severe. Another issue is the water scarcity. So this is again the physical and water systems interacting with the energy system that was analyzed by Clara, our colleague. So just to say a little bit about where we're going at the moment and where we want to go in the future. A lot of the early work, and I mean decades past when integrated assessment modeling was developed, was focused on energy supply. So this is sources of primary energy, fossil and other, electric power generation, supply side options for mitigating emissions, carbon capture and things of that nature. So the big blocky stuff, coal power plants, nuclear power plants, hydroelectric dams, right? But we're increasingly, I think there's an awareness, I think there's been a consensus, and now it's becoming mainstream, that demand and demand side change is really an important tool. It's a critical tool. It's one that we can't leave out in meeting the challenges of climate change mitigation and adaptation. And that was really highlighted in the AR6 report in the individual chapters and overall. So we have sort of helped push that awareness, but we're also wanting to reflect that in our modeling capability. So we really have a focus now on energy services and on whole picture sustainability, right? So not just do we meet the climate target, but do we meet all the other sustainable development goals? So that includes a variety of focus areas and themes that are current across transport and our other sectoral works. So one is about lifestyles and behavioral phenomena as both drivers of energy demand and as mechanisms for potentially reducing energy demand. Another is we have a thread of work on decent living standards. So this is the idea of sufficiency. So it's not great if an entire economy meets a climate threshold for total emissions, but people are living in poverty and in heat stress, or they have no mobility to access employments and amenities and so on. So we're looking at thresholds for energy service needs to achieve those sustainable development goals for all individuals in the population, and how much would it take to bring people who are currently below those levels up to those thresholds. And that's very much related to also distribution and equity of energy use and quality of life outcomes. So to continue on that demand theme, but also talk about community and engagement and networking for research, one of the activities that we have initiated, this is actually with funding from the Japanese Ministry of Innovation, I believe, is this EDITS network. And so this is a global network of researchers focused on energy demand changes, which are or could be induced by technological and social innovation. So this is, all of the things that we've been talking about. It's not simply technological. It involves the social and governance and behavioral aspect of the energy system, but how those could lead to reduced energy demand. And this is building on earlier work on low energy demand scenarios that was led by our emeritus colleague, Arnold Krugler. And so within this project, we're building a research community. We're connecting people from countries all over the world, trying to improve, understand, document, and point to improvements in state-of-the-art modeling on the demand side, how those can be linked to large-scale models like MESSAGEix, and to better inform policy, of course. Right? So just to summarize, I have a couple more slides. I would say we don't have a model. I think it's always a mistake to think about a model as an object that can just be handed over from one person to another. It is rather we have a body of method and practice for model-based research. So research that involves a model, but the model is not the starting or ending point. It's a tool that we use, right? And we need to have a good tool. We need to know how to use the tool. So that body of method and knowledge it's embedded in our research practices, how we create, use, interpret models. And we do have some tools and software that we use to do that, but also knowing how to use those, knowing how to improve those to do new things, right? And then through that work, we do create models, a family of models to do that work. When we think about it this way, we think about where we can apply effort to get us to the places we want to be in terms of producing academically interesting and policy relevant results. So one thing we can do is we can connect to data and models that already represent specific phenomena. So especially as somebody who, I've worked in my grad studies with transport researchers who do very granular agent-based modeling of travel routes through particular cities and a variety of like vehicle scale simulation of how particular hybrid drivetrains function under certain duty cycles and things like that. I know that we cannot include all these details in a global IAM. So we have to work with and understand how the results or representation of those phenomena that are developed by other researchers can be plugged in or used to better calibrate or validate our global and long-term models. Especially important when these are complex cross-sectoral or it's interdisciplinary phenomena. So I think one really interesting one that a lot of people are focused on in transport is the materiality of vehicles, right? So if you are mining critical materials like lithium and cobalt, and these are becoming components in vehicles, the vehicles are going through a use cycle. And then there's the question of disposal, the end of life of those materials. Where do they make it back? They may not even go directly back into vehicles, right? So copper coming out of a used electric vehicle may go into the grid. They may go into a wind turbine, which is fine. It provides flexibility, but it means that you can't understand that through studying only the transport system. So we need to look to existing research that already does that very well. Another direction of effort, as mentioned, and I think you'll hear a lot more from Ayelet and Shahar, is to narrow the geographical scope. So when we're doing things at the global scale, we have to get things roughly right or not too wrong for all of the regions of the world. And that's actually quite hard. Once we focus on a particular country, then we can say, okay, let's really calibrate this very carefully to the actual understood real world state of this system. And the last thing is to design and implement scenarios. So the different calibrations or settings that we run through a model are not, it's not some platonic ideal. It's not dictated by science, but rather it's dictated by the applications and the knowledge that we want to get out of it. So we have to have a real process of generating narratives. What are the narratives that we want to simulate within the model? And so that when we then implement those quantitatively, then the quantitative outputs tell us things about the differences between different narratives that help us understand our policy options and what we want to do. So just to wrap up, this is a model that I think is not, I should say, I personally, as a foot soldier, am not involved in setting up and running these, but I understand from my colleagues who have been with IIASA for a very long time that this is a very successful model of collaboration, which is to have a national knowledge partner, right? And they found that's a very effective way for organizing modeling work for policymaking. So the basic idea is that there's a three-way collaboration. There's IIASA, there's a national planning entity, and then there's the knowledge partner. And so, for example, in the India work that I mentioned briefly earlier, NITI Aayog, the national planning agency, is the national planning entity in that case, and we have specific energy research think tanks and institutes that serve the role of the knowledge partner. In this, IIASA's role is just to provide support and updates on modeling methods and workshops and training. So, some of that information is always there in our publications, in the supplementary information and so on, but it's really to bring the people doing the country-specific work right up and sit them next to our colleagues who are developing and maintaining the modeling tools, so that that body of knowledge of method and practice for doing modeling can be transferred in that way. The role of the knowledge partner is just to evaluate and communicate. So evaluate those modeling methods, evaluate the data that's available, the extent scenarios that are available, and communicate to those other people how they might be used and applied. To guide and facilitate, so that's especially to develop sort of this long-term relationship with policymakers and understand the value of supporting and maintaining modeling work over the long term. To build links with stakeholders, so those can be also stakeholders within country that we at IIASA and Vienna would never be able to identify, but in fact are very crucial to certain discussions. But one thing that we can do is we can say, well, there happens to be somebody in South Africa who's focused on a very similar question. So this is a peer-to-peer connection that you could have with them without us needing to be in the loop, because that distributed peer-to-peer communication is very very important. And then finally, it's just to host and maintain the model and tools. So the model tooling to set up, implement the scenarios, post-process the results, produce those quantitative results that are useful as policy inputs, needs to be actively maintained and kept up to date with the latest changes in the global model framework. And so that needs a continuous stream of maintenance work. And it's often great if the technically skilled people at the knowledge partner or identified by the knowledge partner can do that. And then it also produces outputs in terms of academic work and peer-reviewed publications. So sorry, I ran over just a minute or two. We do have some IIASA EC activities. I guess most people are aware of these, so I don't need to belabor them. And maybe Ayelet can say a little bit. Yeah, okay. So I will not say anything I will not steal Ayelet's thunder and talk about the MESSAGEix single country model. But there was work we did with Ruslana. So she was somebody who came and spent some time at IIASA, and this was about analyzing climate pledges and the notion, the policy idea of an Israeli Green Deal. And then there's been a collaboration with Tomer Fishman. Again, I have not been involved in this. Barry could probably say more, but this is about, again, across sectors. So materiality, so the industrial production of materials, steel, cement, and so on, and the use of those to provide buildings, which is the housing and residential sector, which requires an input of materials. And so as part of this, they developed some new methods for sort of extracting buildings materials intensities at a global scope with sort of fidelity to the different conditions in different countries and building practices and so on. That was correct. So yeah, just some examples, and I think these are sort of seeds or sort of like flashes of what a fully fledged knowledge partner would be doing a lot of these things simultaneously, continuously. Right? So that's all that I have. Thank you so much for your attention. I'm sorry for speaking so long, and I hope we can have some good discussion afterwards. Thanks.
Thank you, Paul. Some of the topics that you mentioned in the discussion, but I would just say that we have other, so the Ministry of Environmental Protection, which could not attend today, is also working on the gains for Israel,
Okay.
And then specifically to what you mentioned about the buildings and the materials. This is very relevant to Israel. So Israel is a very unique economy. When we bring everything from abroad, we don't have almost no national resources, natural resources. And then not losing those materials again, you know, the lithium and the cobalt and all of that is a very important task for the economy, which does not happen at the moment because our recycling industry is also very, it's growing, okay? It's still not stable, and we are a small scale country. So that's something also to remember. So this is something very relevant that we plan to go, and we have some Israeli data on that now. So same with materials, the same with buildings. So Tomer was doing more of the generic one and the global one, and now we really want to find these ways to actually get more of the Israeli data into those models. And before we move to Ayelet, which is really will show us the Israeli model and the specific, I would just say that one of the key strengths of this collaboration is really to be able to be like a role model for IIASA, taking this one specific country, which is very unique in many aspects, like an energy island and small scale and natural, very limited natural resources, and apply those models to the full extent as much as possible with as many modules and sub-modules, which will take time, and also adapting this, I would say, the model that you show on the knowledge partner and the government is very important, and that's what we strive to. So, Ayelet, this floor is yours. Let me just change your presentations. Okay, so we have like 15 minutes. So until 11 minutes.
Okay, thanks, David. Okay, so I'm Ayelet, and I conducted postdoctoral research in ECE program in IIASA, and we were focusing on the national level of the energy market. If I'll have time, I'll speak about the other national MESSAGEix and the policies that were involved in our research. But I'll speak now about as Paul mentioned, about the transportation model. The project is led by Vered, with Paul from IIASA, and Anat, Jetnik, and Rotem are responsible for the survey, and Odelia is a software programmer. So before I'll speak about the transportation model, I want to, as already Paul mentioned, we will speak about the MESSAGEix model and how it is modeled with the transport model in a detailed model. So when we are coming to develop an Israeli model, there were 3 steps that we had to implement. So the first step was to take the global model, or as the message global model, and to develop with data of the message global model to a country level data set. And the output was the preliminary baseline scenario. The second stage was to put the different scenarios and the different data with the help and assistance of stakeholder engagement for a country-specific data set. As we have mentioned, Israel as a small island with energy and population and GDP that are the growth of population are not similar to other countries, and to set the country level model, and the output will be the refined baseline scenario. And then after running the model, the different mitigation scenarios, we will, the output was the mitigation scenarios. So as you can see, the MESSAGEix model is quite similar to describing a whole energy market, from primary energy to infrastructure, in the energy sector, with the last even for lighting or condition, and with the 6 demand sides of industry, residential, commercial, and transport. And the message model is getting feedback from the macro aggregated macro model, is a iteration of supply and demand. So, and now I'll move to our project that we are now researching, the modeling behavior of consumer preference for alternative fuel vehicles and its energy demand implication at the national level. So the objective of this project was to analyze the future energy transportation in a national level. And what we actually wanted to do is to put the micro and macro together by examining the diffusion consequences for various alternatives of fuel vehicles, and how it is conducted and implemented in the energy and the environment. And if we speak about the message model, we are speaking about on one side. I'm not going to speak about the IAM integrated assessment modeling, but we want to also to identify and to bring consumer preference of multi-segment discrete choice modeling that are sometimes are not monetized or not financial, and to put together from one side the national, the techno-economic model, and from the other side the passenger transport representation. And we've done that by 2 methods of one method and logic-based model. So I'll speak a little bit about, I mentioned in the flash about the survey. Rotem and Nanat, they are responsible for that, so they did all the work. So the survey is a based analysis of consumer preferences, choice modeling, that is based on discrete choice experiment. After implementing the survey, we are integrating the results of the consumer behavior survey into the message energy model. And the last step will be to examine the diffusion consequences and the implication. So only a brief view about the Israeli transportation overview. As you can see that in the year 2021, there were 10,000 new electric vehicles in Israel, and it's rising and rising.
20. Where do you see 21?
At the bottom.
At the bottom. No, because no, I didn't put the whole because I didn't have the whole 2021.
All the data of
but,
the 2021.
yeah. So as already Paul mentioned, when we are coming to putting from one side the model and from the other side the scenarios, according to the Israel National Action Plan on Climate Change, as you can see, there is we want the reduction of the pollutant from transportation, and to implement that, we need to reduce annual average private car mileage per citizen from 5,000 in 2018 to 4,000 in 2050, and also to shift to a more sustainable transport from 37 in 2018 to 70% in 2050. Other scenarios are also to move toward the zero emission vehicle by reducing the GHG emission of new LDV vehicles. And we are planning also to the third scenario is to mix between the two scenarios. So I'll speak about the Israeli transport model that is derived from the Globium transport model. We are now concentrating only on the LDVs, light duty vehicles, with 5 main propulsion technologies in the market. The LDV demand reflects a heterogeneous set of consumers, and I'll speak a bit about the disutility cost by modernized and non-cost vehicle parachute. So here you can see a diagram of the transport model. We have 5 stages of input data and assumptions. That's the data that are derived from IIASA scenario dataset, data from local data from our datasets like ICBS and other ministries. Input data processing after the data is implemented. We are processing the data for the share of consumer groups, for LDV, and we have also data for non-LDV transports. Then by the model pro, and afterwards the post-processing and the output of the results by the disutility cost, some techno-economic parameters, and passenger kilometer traveled, and other different of change in demand. So I won't get this is the different data that I want to speak but a little bit about the disutility cost that was derived from the survey. So vehicle choice depends more than just on techno-economic consideration. So when you want to buy a car, the consumer have consideration about the financial and non-financial attributes, and both are influencing the choice of the purchase. So financial consideration are really up forward, like capital costs and exploitation, but the non-financial attributes are not for the perceived risk. For example, the vehicle range anxiety, if we are speaking about electric vehicles, and recharging station availability, and so on. Here are examples of the financial and the non-financial parameters. So the survey process was in 4 stages. I won't get into all the stages, but the final stages was with a N of 1,000 and 4 parts questionnaire. And what we've got is 4 clusters of groups, with for each cluster of group with 5 population of vehicles, and different parameters. Some of them are financial and non-financial, and all of these modes or demands are put into the model, and the model of transportation, and are derived together with the MESSAGEix model. Stop here.
Yeah.
No, I wanted to speak about the answer, but
Okay, yeah, let's stop. So we
Yeah,
have enough
because
time
it's,
for others. Okay, so thank you, Ayelet. This is still work in progress, so it's not that we have already results to show and all that. And it's been actually important to say that this is a very also interactive process between the IIASA people and the Israeli researchers, because you go a step forward and 2 steps backwards, and it takes a lot of effort. And that's why also when Ayelet was sitting there as a postdoc for the first stage, it was very helpful, because something happens, you just open the door and you get next door to the one that knows all the details and make it work. So so this ability of moving, and going to IIASA actually for a few months, for a year as a postdoc, is very important, especially at the beginning, when you just want to get going and understand the modeling environment. And this is also a project that when it will end, it will also show the inclusion of the social sciences very, very strong. Okay, so a lot of interdisciplinary approach with researchers that comes from different disciplines, which is quite challenging to put it all together at the end in numbers and within the model infrastructure. But let's move to Shahar. Yes.
Before Shahar, the output of this this would be some kind of recommendation. I mean, it would be a path or a recommendation for the government, what to do, how to encourage people to buy something, or so that would be the.
So this at the end, it's as Ayelet started, it's top down and bottom up. So you have the micro level of the consumer behavior and choices, and then you have the full national energy market, and you want to see how this connects, right? So if now everyone wants electric vehicles by tomorrow, what does it mean for the system, right? And then the output is still at the end the message output on what does it mean if consumers going to choose this or that, okay? How it will affect the market.
The Israeli government had a decision that until 2030, they will sell only electrical vehicles.
Right. So this is modeled as part of, as part of the scenarios to see what is at the end the output of the energy market, the emissions level, everything, and would you meet the policy scenarios that you actually model? So it's not about transport as a transport alone. As on the way, as we do the surveys, for example, we publish papers on the surveys findings and all of that, but this is really just small part on the way to be able to at the end bring it back to the main energy model and see what does it mean, the full system consequences.
Yeah, the main problem is that we are not prepared for this. I mean, the electrical, we are not prepared for the 100%.
That's why the technical part and the engineering part is also important.
To add to what Vern said, that's why we are putting together also the message model. The message model is taking into account technological and economic considerations, and by the model we can say if it's suitable, can we implement it in Israel or not.
Shahar, why don't you?
Okay.
Yeah, we just stop. So now we will hear Shahar, which is from the Ministry of the Energy Ministry, as the policy strategic partner and stakeholder in the development of the message model, and what we plan to do next, because we have the original version of the model, which was calibrated with 2015 data, and now we want to move forward to be able to look at new ambitious policy measures the government is putting together.
Yeah, so regarding to the message model, I will show even less than Ayelet, because we just have started the interacting with the message model. We just finished the preparation stage, so I will mainly talk about the preparation stage. So the target was to have an energy model for net zero emissions in Israel by 2050. This is the target for the energy sector. There are other sectors, of course, but we are in the energy ministry. Myself, I'm Shahar Dolev from a strategic division, long-term planning. So I'm looking forward towards 2050 and how we can reduce the emissions from the energy sector to zero by then. So we are facing several global trends in the energy sector, which give us some direction into the future. The first one is that the electricity sector becomes distributed. If usually it was several power plants producing the electricity and bring it to by transmission network to the customers. Now the customers are already also generating electricity. They have batteries, maybe electric car that can take energy, maybe send it back to the grid. Everything is now distributed and smart. So the face of the energy sector is changing, and we have to adapt to that change and use it towards our goals. The other aspect is the technology disruption. What we see here is the graph of the cost of solar PV. We see the price drop. So even without any clean energy targets, people are going to switch from fossil fuel usage for electricity and energy to new kinds of energy like PV solar, maybe wind. In Israel, we have very little wind, but mostly PV solar. And this technology disruption affects the energy sector. And last one, of course, more special is the climate crisis that forces us to reduce the greenhouse gas emissions. And the energy sector is one of the main sectors to emit greenhouse gases in Israel. So we have to set our target with the global aims of net zero by 2050. Okay, here we see the countries that set net zero targets. Already about 88% of the countries in the world, and Israel currently only stated that we are going to achieve net zero by
By
2050.
2050.
Yep.
Yeah.
But we didn't yet publish official pledge for that. We're working on that. We wanted to publish one before the COP in Sharm el Sheikh, but we couldn't do it. So I hope that in the coming month we will have such a decision. We have new government, new minister. So I guess one of these targets is to give such a pledge. Okay, so what we did previously, we did some work only for the electricity sector, and we created our own proprietary model for the electricity sector that tried to look at the possible options in Israel to increase renewable energy in the grid. In Israel, we are kind of in special condition. First of all, we are an energy island. We cannot get electricity from outside when we don't have enough. We cannot send out when we have overflow. So we have to set everything within our borders. We also have almost only solar energy. There is very little wind in Israel. We have problems with bird migration and other flying animals like bats, etc. And we also don't have hydro. We don't have geothermal. So mainly we'll have to base our future generation on solar. And solar is very hard to integrate into the grid because it comes in a certain hour, and so we have a lot of it more than we need at noon time. We don't have anything at night time, and also there is a problem between the summer that we have extra energy and the winter where we have deficiency. Yeah. And transferring the energy from the summer and spring to the winter is very difficult technically. There is no known way of transferring such huge amounts of energy. People talk about hydrogen, maybe generating hydrogen from the excess in summer, storing it in underground storage, and then using it in the winter. We still have to see that working, and the efficiency and the cost. It doesn't look very promising currently. So we have a problem with only solar energy, and we'll have to use a lot of storage. So we tried to see how is the balance between solar and storage, and the model showed us that up to about 80%, 85% solar energy in the energy mix. Everything is about linear. If you want more energy, clean energy in the mix, we just put more solar panels and put more storage. But at about 80%, things goes different. It gets out of linearity because we have to begin transferring energy from the summer to the winter.
What is the level of renewable energy in which you must have storage? But currently we don't need storage because we're not reaching.
From about 20%, 30%, you need a little bit of storage, and then it goes up more or less linearly, up to 80, linearly up to 80%.
Up to 80%.
Yeah, and then it goes up very dramatic because you have to start from gigawatt hours order of magnitude to terawatt hours to transfer energy for a whole week from summer to.
My next question, like, is it considering the storage possibility of within day or between days or between seasons?
Within days, until about 80%, you will need within days storage.
80%.
80%
only within days. You don't need interseason.
No, no, until 80%, you see everything is linear. But then you feel the daily cycle, and you have to transfer energy from the spring, actually, to the winter. So we set our previous targets. It was in 2021 at 85% reduction of GHG emissions. And we draw two pathways. The solar pathway says we will use solar energy to reach our targets, and of course storage, and we will get 86% of storage in the energy mix, of solar in the energy mix, and that will give us our reduction targets. The other pathway was, we called it technical path, where we said we'll have only about 50% solar, but we will reduce the other portion of GHG emissions by some new technologies that are still in development. So now we are going to go the extra mile to 100% reduction and specify these technologies. Okay, so the follow-up work for 2023, first of all, it will include all the sectors of the energy segment in Israel, which is electricity, industry, and transportation. In the electricity sector, we'll try to maximize the generation from renewable sources. In the industry sector, we will try to electrify as much as we can and use hydrogen where we can. In the transportation sector, similarly, try to electrify as much as possible and use hydrogen where we forecast that there will be a problem to use electricity.
What hydrogen technologies are you using in the industry?
In the industry?
Yeah.
For heat, for the biggest facilities that needs either very high temperature or very big facilities, it will be difficult to electrify. Most of the industry can use hot water or steam that can be generated from electricity. But there is a very small segment in Israel. You don't have huge, heavy industry. So there is a small segment in number of facilities. This segment uses a lot of energy, about maybe 15 to 20% of the energy requirements of the industry sector. They will need either very advanced electrical facilities that are only starting to see today, or they might use hydrogen.
Hydrogen through pipes, or is it hydrogen because it's important?
We are still not setting targets for that. It might be a localized need, so only local generation of hydrogen and local usage near the facilities, or we might need national infrastructure to transport.
Completely change the wage bill of the plant if we're talking about local storage or internet or national pipelines, right? It's completely different.
Yeah, currently we don't exactly know which industry will need that hydrogen. Maybe only about, let's say, 5 to 10 facilities will need hydrogen, maybe more. We will see it as the technology advances. Like we see in the transportation sector, today everybody is talking about hydrogen vehicles, trucks, even private cars.
SUVs.
But, yeah, but as we see, the battery industry is advancing very, very fast. And my personal view is that in a couple of years, we'll see only electric cars. Also, the heaviest trucks will be electric, battery electric. So maybe in the industry, we'll see a similar trend that the electric technology will advance and will give us solutions for even the biggest factories, but maybe not. So we are having two paths to the future. One which is mostly electric, and the other that is mostly, not mostly, but more hydrogen in the energy use mix.
You said trucks with batteries, with
Yeah.
lithium battery.
Tesla is now showing their first semis. They say it's going to go 800 kilometers fully loaded, only with batteries. That looks like enough for Israel, I think. So I think that in a couple of years we'll see that all the needs in Israel for transportation will be met by battery electric options. In the industry, we are still less sure. So we see a small portion of hydrogen even on the most electrified path, but that might change. We'll see in the coming years how the
You and Volvo will disagree with you.
I know.
We need to finish.
Yeah. So let's go on. We are considering about 5 paths to reducing the emissions for the energy sector. Of course, first one is use renewable energy, solar and wind. The other one is use hydrogen, either green from solar or wind, or blue. Blue is using natural gas to generate hydrogen and capture the CO2 emissions. So carbon capture and usage or storage will be might be a central part in the energy future. We're also considering nuclear energy. In Israel, it will take a lot of time if we are going to have some nuclear plant, probably beyond the 2050 horizon, but it might be an option for the long run. Biological and synthetic fuels, mostly for shipping and flights, and the import of clean energy. Yeah, thank you. The import of clean energy, it might be electric cable, like we're now working with Europe to connect the Israeli grid to the European grid. It might be a pipeline of hydrogen. Egypt, for example, they're positioning themselves as a major clean hydrogen exporter for Europe. So maybe we can also buy some clean hydrogen from them. Also, it might be clean biological and synthetic fuels, maybe ammonia, a lot of talk about that. So this is the field.
Or from Jordan, we had an agreement.
If they are going to generate, yeah.
For one last minute.
Yeah, okay. So we were looking about 5 paths. These are like the boundary scenarios that define an area of like a pyramid, as you see in the image, that defines the boundaries of our options. And we think that the future path is not going to be any one of them, because for any one of them, there are very severe limitations to reach net zero only by the solar or the blue hydrogen or the nuclear, etc. So the future path probably is going to be somewhere in this pyramid, taking a little from each path. And we want to use the message model to help us find this optimal path.
Just
Introduce yourself.
Lucan from the Hebrew University. Regarding solar panels, do you have an estimation of how much land
area,
we
yeah.
will need to cover, and if your model takes into account the special allocation of available lands and radiation?
Okay, so our model doesn't take the available land. First, we look at the demand. So if we want to go only through this renewable energy path, we will need about 1.5 million dunams of solar panels. Now, there was a work of the Environment Protection Ministry that said that there is a possible for about 800,000 dunams for a solar area over roofs and shades over, let's say, parking lots, etc. So about half of it can be dual use. And now we are entering the dual use of agrivoltaics to have panels over agricultural land, active agriculture fields. So that also might give us several hundred thousands of dunams of solar panels. So in very, very broad terms, we might achieve this target of only using solar energy. But as we see it today, it's very, very difficult. And we struggle a lot, to reach our target of 10%. So achieving 100% will be very, very difficult in this time frame. So we are looking into this other path.
Okay, I suggest we take a break of 10 minutes, just so everyone, even less than 10 if possible, because we're a bit late. There is some refreshments outside. Water is back, so you can use the restroom here nearby. And you had a question, or?
I have a question, but I can ask.
Okay.
I have so many questions.
Great.
לא, אבל אם אתה רוצה.
חשבתי שיש לכם תוצאות. לא? יהיה? לא יצא תוצאות.
כי אנחנו בעצם המודל נטיקס זה מודל שהוא יודע לקרוא הוא לא יודע לקרוא השני אצלנו לא, סקר העדפות, סקר העדפות של צרכנים. גם הסקר עצמו הוא רחב, על המשאבים,
ומצא למצוא אותנו בלב שלו.
אתה מדבר, מה אתה מדבר, איך המושג, זה לפחות את תחילתם. זה מכיר במנהלת רוח, זה 8. בסדר. זה בעייתי. כן.
אני מאוד דוקטורנטית בהכנסות. המודל כזה, אז איפה נכנס למכאן? בין אם זה תמריצים, אני הייתי רוצה לראות את המודל
אז אנחנו בודקים את זה כרגע לפחות מול השטח
What's the actual mechanism of operations there? So funding, or does both sides have to be funding? Do you work together?
I think it varies, right? So in the case of the Lebanon and Uzbekistan examples, in that case, I guess those country governments had the desire, but they didn't have the resources to support. So the Global Climate Fund was one mechanism where I guess we and they applied jointly, and the fund released some money that was mostly paying for our staff time, for some of our colleagues to go travel there, meet with the stakeholders, meet with some local researchers, do a lot of the modeling work, right? I think there are some, like for instance, in the collaboration with Ayelet and my time is supported from the IIASA core budget, and Israel as a member country is supporting the core budget of IIASA, right? So this is one of the benefits that Israel gets as a member country, is that some amount of staff time will be spent for this kind of thing. But once the scale gets larger, then it really is needed that, for instance, a certain postdoc or researcher could get funded from really any source, like internationally or within Israel, to come spend time at IIASA, or to be still sitting here but spending their time.
Okay, let's continue.
So there's a really wide variety.
But way to elaborate, you guys, even if we had funding on this side.
Yeah.
Who would pay for the time on the IIASA side? Would there be funding for that?
I think there would have to be, yeah. So for example, right now we have a visitor from Japan, from Toyota Motor Company. So they were really interested in using MESSAGEix for their analysis and strategic purposes. They sent somebody to come and work with us for 2.5 years. On top of that, they transferred to us something like 3 months.
Okay, let's start. Okay, great. So now we will move to 3 presentations by different researchers in different institutions that are looking at the energy market and energy scenarios in different perspectives. And I say energy and transportation. And we'll start with Dr. Moshe Tshuva from Afeka College of Engineering. He's also the head of the mechanical engineering program there. And we have a very fruitful collaboration with Afeka College in general, exchanging students, doing courses together related to energy. So thank you, Moshe.
Nice.
Yes, please.
First of all, I would like to ask you to ask me questions during the presentation because I'm used to be, a teacher, and then my students all the time interfere. So I would feel a little bit awkward if no one will ask. So this is a presentation of a work that has been done as the master thesis of Ronen Eran and also of Lev Zivin. Dr. Gur Mittelman and me were their instructors, and we also used the help of Ohad Heisenler, Dr. Ohad Heisenler and Dr. Yossi Luzon in putting all the Python and all the integration of the system. I will show you later. So the background is that Israel said that the target is to get to 2050 to 100% renewable energy or 100% reduction in the carbon. Up to 2021, we got to 8%, and 2025 we will get to 17%, and maybe in 2030 we will get to 30%. That depends on the situation. So we were focusing. The work was focused only on electrical energy, meaning how can we reduce the emission that is caused by the production of electric energy. So that was the focus of the work, and we did develop a holistic approach in a way, something that was contradictory to your work. We did go inside the details of the input data. We had a model. And let's say about the input data, we were looking on all the aspects of renewable energy. We were looking on the demand, the expectation of demand, did a detailed evaluation of the renewable energy sources in Israel. And eventually we tried to maximize the amount of renewable energy by minimizing the amount of fossil in 2050s. So that's part of the study we did. Ronen Eran did a lot of literature review about the different models. So there were problems with the weather broadcast because there were different types of weather broadcast, and they were a little bit they were not accurate. They were not going together. Solar and wind, the storage, there weren't any detailed about the market limitation. The model was hourly, just like Shahar mentioned. So we did an hourly model, and but not all of them were dynamic and not the complete planet. And the management model was not a system analysis model. So we tried to do, and there was no full system integration. So what we try to do is we try to do a full system integration. Of course, we were talking about time step of 1 hour, meaning taking the whole year and looking at each hour every day of the week. No limitation of grid development, that's a problem. That's a problem in Israel because we don't know, even to 2030, we are not sure that Israel would supply the right grid to even supply the energy for a vehicle, for electrical vehicle. Israel is an island, as was mentioned, so we took Israel as an island, and we looked only on the energy production, renewable energy, only according to the green line, meaning we didn't look on the Gaza and on the West Bank. There were only demand, but we didn't look as a supplier. We didn't took them as a point of supplier. And that's the model. That's the old model. So at the beginning, we were looking on the renewable energy resources, the type of resources that we can use, collecting all the area. Ronen Eran and Lev Zivin did a very exact work in taking every part of Israel, using the GIS of Israel, looking at every part, what are the areas that are available for production of renewable energy. And as Shahar mentioned, most of the energy would be PV, would be solar panels. We were looking on hourly weather, broadcast, wave data, also the wind data. We were looking on waste data, and the reverse and renewable energy that we were talking about was taking an industrial data from companies that sell, let's say, solar panels. We took the solar panels and tried to match them. So that's the input to the model. As I mentioned, it was hourly. And then we were trying to do some energy management system model in which we will have the demand. In one hand, we will have the hourly demand, the storage capacity. That's a major problem. That's the major problem of renewable energy in Israel. The storage, the ability to store energy. And we were trying to minimize, eventually to minimize the fossil energy. So I will show you in a minute. So we took, as I mentioned, first of all, we were looking on the solar panels. The total area of Israel is 21,616 square kilometers. Out of it, open area of 1,229 kilometers. Israel has a lot of natural resources and a lot of military areas in which you cannot put any solar panels, you cannot use it. We were also thinking about the agricultural area, solar agro as a potential. So we have about 4,000 square kilometers of agriculture area. In those areas, you can use the GIS of Israel and see exactly what kind of plants are being in those areas. So we have some kind of crops that will gain from putting solar panels, because solar panels would reduce the amount of heat, and then we will have more production of agriculture. Some of it will gain, some of it will be natural, and there are parts that will lose because they need all the solar energy. So eventually, what we're trying to do is trying to suggest also some kind of integration of agro photovoltaic. And we wouldn't use the 24 latitude, the angle of 24 degrees. We will use 40 degrees. By doing so, we will reduce the influence of shade on the crops, but then we will gain electricity. And eventually, what the conclusion is, out of this 1,000 square kilometers plus 367 square kilometers, we can gain something like 132 gigawatt of electricity. And from agro photovoltaic, we can gain something like 40 gigawatt. That's the potential. We wouldn't use all of it, but that's the potential of Israel in 2050s. We were talking also about the potential of wind turbine. That's a map of the Israeli meteorological. So you can see those are the areas in which the red is the areas in which we will have enough wind at a height of 100 meters. As Shahar mentioned, we have a problem because Israel is a place in which about 500 million birds fly from the north to the south and from the south to the north during the during the year. So it's a problem, and we are not sure that we can use it. We used the Erez Perry work to try to figure out what are the areas. It's mainly on the north. As you can see, mainly on the north, we can put some wind turbine. And we were trying, Ronen did a very excellent work in figuring out what kind of wind turbine would suit these areas according to the different wind speed and the production of electricity. So as you can see, we are not talking about a lot of energy. It's 1.93 gigawatt onshore. Ronen and Lev did suggested that we will try to work also on the offshore, mainly offshore of Haifa. We can put also wind turbine offshore. There's a very good wind there, and there wouldn't be any problem regarding. Kind of wind. Yeah. Okay, but that might be also a way to produce a renewable energy. Okay, so as I mentioned, there were different places in which we got different information. So eventually we used the PV GIS data set to find out what are the wind production, the wind speed in the different places in Israel. We were trying to figure out if there's a possibility to produce electricity using the sea wave. So also we were trying to get information from the Israeli Sea and Lake Department. They gave us the information about sea waves, organic waste, and the design was very accurate. Okay. According to the wind, we were trying to figure out that that's the offshore, so I'll pass this offshore, but there are places in the economical sea of Israel that we can put also wind turbine over there. The waste is very small. The amount of energy we can produce out of waste is very small, as you can see, 0.35 gigawatt. I mentioned the model. We used the SAM of NREL to calculate the amount of energy that we can produce out of solar PV. The battery, most of the energy we will get eventually using the vehicle. Meaning the vehicle would be a sort of moving batteries. So the storage that we will need, it would be this amount. I'll show you in a minute. So the input to the model, I will go briefly. That's the demand. We need about 160 terawatt hour in 2050s. And if we will add also the demand for electrical vehicle, we will get up to 180. I think that's the next slide. So that would be the demand for electricity. And eventually, we will have to have also fossil power between 25 to 31 gigawatt. We wouldn't use it all the time, but we need it as a backup because of the problem the problem of storage. We looked also on the storage, hydro storage. We have about 8 gigawatt, 3 of them already working in the Gilboa, and some of them are under construction. And as I mentioned, it would be vehicle to grid, meaning we will use the vehicle as some sort of storage, moving storage. That would be the solution. Of course, we wouldn't use it all the time. We are only talking about 30% of the storage of the vehicle. And okay, and we were talking also about some stationary batteries. So that's the model. The entrance is the renewable energy during the interval T, that's RT. DT is the electrical energy demand. So that's the possible energy production using renewable energy. DT is the demand in that interval. ST is the amount of storage at the beginning of the interval. And F maximum, that's the that's the maximum fossil power that is available for us. And FT, that's the production of this mathematical model. The production is the amount of fossil energy at that time of interval. And of course, the storage at T+1. And we were trying to figure out what is the minimum FT, meaning the target of this computer program was trying to figure out what is the minimum FT. Eventually, the results is that we were trying to figure out 3 scenarios. In 2030s, that's the work of Lev Zivin. We were talking about 25.6 gigawatt of renewable energy and 11 gigawatt of fossil energy. The storage capacity that is required is 60 gigawatt hour. And the renewable share can go up to 47%. So we can achieve this target by 2030. 47% of the electrical energy in Israel could be renewable energy. We will have to do some dumping because in the summer we will have much more energy than is required or we can store. So 13% will be dumped. And the fossil capacity factor, meaning the time that we will use the fossil, would be 54%. Now we were trying to figure out 3 scenarios for 2050s. Scenario A is 172 gigawatt of renewable energy and 31 gigawatt of fossil. Then we will need 216 gigawatt hour of storage capacity. We will have 88% of renewable energy, but dumping 46%, that's a lot of dumping, and the factor is very low. So we tried another scenario in which we will use only 86 gigawatt of renewable energy, 30 gigawatt of fossil, and the same storage, but then we will get to 80% of renewables share, but only 4% of dumping or 5% of dumping, meaning we will use all the renewable energy. And of course, the factor of the fossil would get up to 13%. I asked Ronen to do also the extreme one, in which we will get to 100% renewable energy. As you can see, we can get up to 99.5% of renewable energy, but it would demand a huge storage of 500 gigawatt. That's a lot of storage. And of course, we will still will need some kind of backup of fossil, but then the fossil capacity factor would be very, very low.
Tshuva, it looks good to me that you still have 30 gigawatts of fossil.
Yeah, as a
Even
backup.
with that
Yeah.
much of storage, you have to better your.
Yeah, that
storage
probably. I did ask
So let's try
Ronen.
to,
I did ask Ronen to do it on the last minute, just before he hand over the work. So maybe we will need to work on this work. So you want me to?
yeah, I want to
Okay,
give
so
room
that's-
for
that's
discussion, how we can take your walk
Okay,
and
so
think
that's-
about it in the message
that's-
context. So it's not to stop you, it's just
Okay.
to allow the discussion.
So that's a typical January 2050s, as you can see. That's a typical week during January. That's the problematic month. So you can see that's the demand. The demand is on this. That's the demand. This is the night hour and the day hour. So demand would rise and then go down and again. And of course, the yellow, that's the renewable energy, mainly using solar PV. And the storage would go, that's the battery. So the battery could go from 90% to 15%. You cannot charge it more and you cannot dump it, empty it lower. So that's the battery. I will go to the conclusion. Yeah, that's the one. So eventually, if we will take the scenario that we are expecting to get to 80% renewable energy, solar would be 57%, solar agrivoltaic would be 17%, fossil would be about 20%, and the rest would be some kind of wind and waste and wave and so on. Of course, it depends on the storage. If there would be solutions for storage, then we might solve the problem and get to 100% relative renewable energy by 2050.
Great, thank you. So Paul, maybe you can think about a few things on like, when you get bottom up daily, and season, while some of the messages, we are limited on the granulation, and also the integration of GIS and location specific.
Yeah.
But I want to actually move to Irena and then go back to the discussion. I'm just pointing out because Irena will actually talk on some of the things related to storage, right? And the study that they did from economic perspective. So I think it will be a great continuation to look at the things from the economic angle.
I have a question about the dumping. Why can't you use this energy for desalination or for producing hydrogen?
Yeah, it might be, but we didn't consider it. Yeah, it might be a solution for producing hydrogen or so on, but we didn't consider it.
You have to have extra capacity of desalination ready for these few hours in the year.
No, maybe hydrogen, production of hydrogen, green hydrogen might be a solution, and then
You
it
have
could
to
be
store
also
it.
storage for, yeah.
Okay, so just to let you know, so all the groups are a bit behind. We're gonna go back to the room at 12:45, so secure a bit more time, but then really let's try to really be on time here with the last two presentations, so we can have a bit of discussion. And again, this is just just to start, we will continue that, but thanks, Irena.
Hello, I am going to present our recent model with three generating technologies: photovoltaic, battery storage, and gas turbines for competitive electricity markets. My co-authors are Professor Fischler from Tel Aviv University and Professor Wu from Hong Kong Education University of Hong Kong. A couple of words about our motivation. We see that the most of the countries are determined in their commitment of decarbonization, and this required a large-scale deployment of renewable technologies. And we know that the main problem with renewables that there supply uncertainty. That is, it's not enough to build the capacity. We depend the actual production depends on weather, on hour, and so on. And that's why energy storage with a battery system, for example, is an important component of flexible capacity. In our model, several words about assumption, 3 generating technology, batteries, PV, and natural gas. We assume that during the daytime hours, we use PV and gas, and during we can use, and we check, with the, we will do it. We can use PV and gas, and during the nighttime hours, we can use batteries and gas. The market structure consists of two types of firms, and identical firms employing PV and batteries, and them identical firms employing natural gas. We divided 24 hours of the day on 2 sub-periods, daytime hours and nighttime hours. And our planning horizon is 1 year. We assume 2 constant and known rates of the sun radiation. It's low in the early morning and late afternoon, and highest around noon. For simplicity, we assume only 2 rates, omega-1 and omega-2, and omega-1 is lower than omega-2, reflecting that PV effective capacity is low in the early morning and late afternoon. There are 2 hourly electricity demand functions, one for the daytime hours and another for nighttime hours. I'm not going to explain the mathematics here. We don't have time for this. The annual costs a function of firms employing technologies, PV technology and batteries is linear and consists of fixed and variable cost. We also, it's known that the variable cost is very low, and we can assume that it's close to 0. The similar function, cost function is for the firms of employing a natural gas. And our model is 2-stage model. The first stage is building capacity when the producers maximize their annual profits for a 1-year operation horizon. The second stage is operation. The producers choose output that maximize their operating profits given their capacities. The frequencies of the stages are very different. The first stage decision is made once in a year, and the second stage decision is made every hour. We solve the model recursively. That is, we first solve the second stage problem, which is for no competition. There are 864 possible solutions, but only 86 of them are feasible in the sense that they are consistent with the rational behavior of the firms and the independent system operators' dispatching procedures. For example, we exclude solutions in which the firm employing PV and batteries sells electricity to customers and charges batteries during the both daytime periods at less than full effective capacity. Then we insert the 86 second stage solution into the first stage objective function and obtain 86 first stage analytical solutions. For numerical simulation, we used a VBA program to quickly check the values of all the first and second stage solutions, finding that only 3 to 4 admissible solutions exist for each data set of 19 exogenous parameters, and only one of them, of 19 exogenous parameters, and only one of them is optimal. And now I'm going to demonstrate the main result of the model using the Israeli hourly electricity law, which is projected for 2030. We also run the simulation to until 2050, and then we have a very close scenario to your B scenario. It's exactly the same for PV and for battery storage, but it's only fifth of the gas.
Okay.
Here it's for 2030. We took the actual load in 2021 with a 2.8% annual growth rate in demand for electricity. This figure presents the industry capacity as a function of the capacity cost ratio of batteries and gas. In this ratio, theta B to theta G. In this ratio, only theta B, the cost of batteries is changed, and the gas fixed cost is constant. When the ratio is higher than 0.2, no batteries will be deployed in the market. When the ratio is lower than 0.1, the firms employing the natural gas technology exceed the market. In the interval between 0.1 and 0.2, all three technologies are deployed. As expected, the capacity shares of PV and batteries increase, whereas the share of gas decreases and the capacity cost ratio decreases. We see also that when batteries enter, their share is significantly larger than the share of natural gas replaced by batteries. The reason is that the nominal capacity of batteries requires to supply electricity throughout the 14 nighttime hours is about 14 times the nominal capacity of the gas turbines used during these hours.
Your storage levels are not growing linearly with size, right? The storage levels are not growing linearly.
It's 14 times higher. It's for 14 hours of the nighttime hours, and that's why it's just larger in 14 times. It's okay? Yeah. The gas for 1 hour and a battery for 14 hours. This figure shows that the nighttime electricity price decreases from $90 to $44 per megawatt hour when battery cost declines. Also, the electricity price in the first daytime hour decreases as well. In short, cheap batteries are the key to low market prices. Electricity price in the second daytime hour rises when battery cost declines because of the trade-off between electricity produced by PV for sales and for charging batteries that exist in the second daytime hour. I think that it's what you said about the trade-off between PV and battery. In fact, it may be the opposite. The electricity price in the first daytime hour may rise and in the second daytime hour decline if PV capacity is tighter in the first daytime hour relative to the second daytime hour. It depends on on the value of omega 1. If omega 1 is very small, then the trade-off is in the first daytime hour and not in the second, like in this figure. And we also have the graph of industry profits as a function of capacity cost. Cost ratio, the gas using firms are profitable when batteries are costly. However, their profits decline when batteries gradually replace the natural gas technology during the nighttime hours. The main contribution is the analytics of the market's long-run equilibrium of capacity mix, which can include batteries in addition to PV and natural gas technologies, and the short-run equilibrium of generation and price levels. Another contribution is in the analytical modeling of the effective use of the PV technologies over the daytime hours as a function of the sun's radiation. Using Israel as a case study, we showed that once batteries enter the market, they will replace the natural gas technologies during the nighttime hours at a relatively fast pace. Israel can implement renewable energy policies to accelerate its pace of decarbonization. However, carbon-free electricity supply can occur with substantial decline in batteries cost. For this outcome, battery cost should be about 25% of the fixed cost of natural gas technology. However, it may not happen in the nearest future, so natural gas is a transitional fuel for replacing coal in a country's pathway to carbon-free electricity supply. The regulator can encourage the outcome of reducing the cost by subsidies, tax mitigation, and promoting adoption. Thank you.
Great. Let's move to the last presentation. Okay, you are not going anywhere.
You have 1 minute.
Press any button except the power.
No, it doesn't go. That's the camera. How do you go back to there?
I think it's just this one TV, the other's one.
Let's get going and we'll see. Okay, let's look at those two here. So I will power it. Okay. So our last speaker is בת-חן נחמיאס-בירן from Ariel University, and I was actually very happy to learn about that בת-חן work as we were planning for this session. So that's also the power of trying to bring many people from the different disciplines. We find that there are new researchers coming in, and it's very exciting. So thank you, בת-חן, for your willingness to join us. And the floor is yours. Yes, I'm going to try to get this TV going on again.
Not many people know me. I was in Singapore for a while. I did my PhD at the Technion, and then I traveled to my postdoc at MIT, but I was in Singapore physically. We had a very large lab there, and so I came back about 3+ years ago, and so now I'm doing work in Israel. So I'm going to talk about how we are trying to shape environmental friendly mobility policies using state-of-the-art tools. First, I'm going to talk about what we are doing in my lab, Future Mobility Lab. And then I'm going to talk about the simulation environment that we are developing. And I'm going to show you a recent study that we did. And I think I'm going to show you only one because of time limitations. Okay, so in general, we develop state-of-the-art evaluation tools. These are simulation-based tools, fully agent-based, activity-based, that are capable of simulating millions of agents at the same time for a full-scale city or region. The tools were developed in MIT and were adapted to the Israeli environment, and we are continuing developing such tools here. We are analyzing big data sources to understand mobility, but also to inform our simulation and advance our capabilities. We are particularly interested in environmental impact and new technologies, and most of my work is related to automated mobility on-demand systems. We take special care regarding social and environmental justice, as I'm going to show you later on. Gabi here is smiling. We also develop external systems that can communicate with our simulations So this is very interesting to our collaborations. So for example, during the COVID, we developed an activity-based epidemic propagation model, and which communicates with the entire systems. So this is the simulation environment. As I said, it's an agent-based and activity-based. We model millions of agents, and this kind of simulation is a day-to-day simulation. It's not a long-term simulation. It is producing what we call the activity schedule for each individual. And then we combined it with a traffic, with the dynamic traffic assignment model, which can be micro or meso. So if we look at the entire metropolitan area, we look at the meso scale. We use unified data set. We create synthetic populations, including their characteristic and their full features. We model location choice, land development, network and operation conditions, and we use all the information that we have, including cellular data and whatever we have. On top of that, we develop external systems. So specific models, for example, the energy consumption and emission model that I'm going to discuss later on, pricing models, we develop controllers to control an entire fleet, for example, MOD, or mobility on demand, EVs, transit are also operated through controllers. And as I said, we are particularly interested in new technologies. So micromobility, sensors, AV, and so on. So our system is fully modular. It includes, as I said, it is capable of modeling multimodality. It is behavioral sensitive, and it can capture dynamic and supply interactions, which is extremely important when we are talking about such a tool. So overall, we are producing social, environmental, and economic measures. And we did such work in the past in Singapore, of course, and in the Great Boston area, in a city like Baltimore. We developed it for the last 3 years for Tel Aviv metropolitan area. This is ready to be used, and we are developing it for Orlando area. So naturally, I'm going to focus on the energy consumption and emission model. And this model was developed by Gabi, which sits there as part of his master's thesis. So what you see here is actually a model. Where is my mouse? Oh, yeah.
Very sensitive.
Okay, it's a model that communicates with the dynamic traffic assignment model. So the traffic assignment model sends information to the energy consumption and emission models in the form of the characteristics of each vehicle in each road section, information like mule type, the modem, and so on. And it takes the conditions on the road in terms of density, speed, and road type. And then it is, we are reading the emission factors as relying on the handbook emission factors for road transport and methodology, and calculate emissions and energy consumption. The result of such an effort is a heat map, or if you like, consumption, energy consumption and emission map for the entire metropolitan area in a 15 minutes resolution for the entire day. So here, as compared to other tools, we can model all kinds of emissions, hot emission, cold emissions, you name it. And I'm going to show you how we used it in a latest study that we did for Tel Aviv metropolitan area, where we wanted to test the planned pricing policy and also other policies that we would like to test. So First, we replicate, of course, the condition for the Tel Aviv metropolitan area in terms of demand, supply, and fleet composition. And then we applied one scenario which focused on the geographical pricing policy that the Israeli government is planning to do. You can see the plan here. You see, this is Tel Aviv metropolitan area. This is the outer ring, and these are the three inner rings. And you can see the plan in dollars. If a vehicle crosses the ring, they will pay this amount in the morning peak and this amount in the evening peak. And we also tested scenario that discusses some kind of taxation with respect to car ownership to reduce car ownership of the Tel Aviv Gush Dan residents. So here you can see some of the results, selected results. So here you can see the mode choice. So you see in the base case, 64% of the people use car, a fraction use taxi. A large amount of people relatively use walk, 20%, a very small amount use bus, 9%. And here you can see the change in the mode choice with respect to the two scenarios that we are testing, congestion pricing and reducing car ownership. You can see there is not a really significant change in when we are applying congestion pricing. And the reason is, in Tel Aviv metropolitan area, the majority of the movement of cars are inside the rings and not crossing the rings. Okay, so the residents of Tel Aviv are creating their own congestion by taking their car to the grocery store. Okay, so this is why we see only a change of 100K trips. Another reason is that there is no public transportation which is really can compete with the private transportation. But this situation may change and will change in the future when we have the metro and the light rail alliance. So, but you can see a significant difference in when we reduce car ownership at the household level. So what you see here, a reduction in car and a greater share of walk and bike and a greater share of transit. So we can test, actually, we can do a sensitivity analysis and test different levels of congestion pricing, different levels of car ownership reduction. And this is what you see here. We can see it by activity. We can see it during the time of day. We can do many analysis. And what you see here is that for every 5% reduction in car ownership is equivalent to something like 2.5% reduction in carbon dioxide, and only I don't know, 0.3% reduction in carbon dioxide due to every 10% reduction in congestion charging. Here, what I wanted to show you that we can actually look at socioeconomic impact. So what you see here on the left is CO2 emissions, and on the right you can see NOx's emissions. And what you see here you can see here that we can classify individuals according to socioeconomic clusters as classified by the LMS, like CBS. And you can see here level 1 and the poorest, level 10, the richest. You can clearly see that the poorer neighborhood gets higher pollution in Tel Aviv metropolitan area, and we will see why later on. Here you can see that we can actually analyze children exposure to high pollution. So we can, since we know, since we model individuals, then we know that unfortunately children in Tel Aviv are exposed to 0.2 kilogram, 2 kilograms square of PM2.5, which affects breathing diseases significantly, and that has a significant health of their age. Of course, when we run this scenario, this amount decreases, but still very high. This is an analysis of greenhouse gas emissions. What you see here is that the reason why the poor suffers the most from pollution. So they are located practically on the roads. You see that the neighborhood is very close to the main roads, while here, for example, the richest neighborhood are separated by the employment area, so they don't get the pollution very so now we are working on similar scenarios, energy consumption and emission for 2040. We will have the metro lines and so on. The metropolitan area will look very different, and here we plan to add the future technologies like automated vehicles to the system and see how they will impact. Do I have time, David?
No, I want to keep those 20 minutes, so if possible.
Okay,
just,
so I will stop here and I'm not showing you the other example that I have.
You're probably optimistic to think that in 2040 we'll have the metro.
Of course, I'm optimistic, but we want to test that. We want to see what will happen, and we want to see how new technology can actually, let's say, change the situation and also strengthen the efforts that we built such a system. So to see maybe we can serve first and last mile through AV or remote places and so on.
Perfect. Thank you so much. Minutes left, and what I wanted to do is quickly the people that did not present, just to say your name and institution / area of interest and what why are you here, how it's related to your work, and then maybe Paul, you can take a bit of time to reflect, on what we heard. I don't know, just whatever you see the connection, and also let the people and again, it's just to start a discussion. The idea is that we create a group that can continue, to develop ideas together and proposals. So, Colin, do you want to?
Sure. Colin Price, I'm a faculty member here at Tel Aviv University, and I'm also heading the New Climate Center here at the university, which is really multidisciplinary center where we're trying to look for solutions, and we need these kind of tools to look for the solutions, regionally and globally.
And IIASA for many years, right? As
being a student here 30 years ago, I remember it.
Okay, my name is Eyal Sasson, and I'm a PhD student in public policy, and I'm investigating the future transmission grid that will allow achieving the goal of the transition to zero carbon electricity market.
Maybe we'll just cover everyone in the back.
My name is Limor. I'm studying my master's at the post and I'm here just to observe and get some ideas to my thesis.
And Eyal, I'm starting my thesis with the topic of agent-based modeling and transportation.
Yeah.
My name is Leo Gallo. I'm a PhD student here at the Public Policy Department. And when I'm not studying here, I'm an economist. I'm an energy and environmental economist at the research department at the Bank of Israel. We have been developing CGE model, which is the umbrella under which the message models lies, and other models as well. Markel models also. This is under this framework, and it's very important for us to combine general equilibrium models with macro insights. And we think that these types of models are very important.
And also, he's going to work on nuclear energy.
I'm going to work on nuclear energy. As a matter of fact, I'm going to use the model that Irena just showed you, which is an industrial organization model. It is a model that assumes, as opposed to most of CGE and the message model who usually use perfect markets and free markets. the model that Irena is using and which I'm going to implement in my, Irena showed, and I'm going to implement in my research is a model of oligoholistic competition, which is a little bit different. The interaction between the players are different. And so it is something that can be embedded within message or Markov models, within the CGE models. And currently, all of the CGE models assume perfect competition. And this is an elaboration of this from the economic perspective and not from the technical perspective.
Manan Raz, I'm from the School of Public Health in the Hebrew University. I'm an environmental epidemiologist, and I also work on climate mitigation in the healthcare sector.
Hi, I'm Mirav Cohen. I'm PhD candidate at Technion, School of Architecture and Town Planning, but I'm a bit of a strange bird there. I'm at the ecology lab, so I do social ecology research, focusing on resilience using COVID-19 as a case study, and looking at trying to understand how to measure resilience, which parameters to look, and how to quantify it, using both hopefully quantitative and qualitative information. But basically, I'm here because I needed to choose. Honestly, I wanted to go to all of the panel discussions, and that's why I asked if they're recorded. But in my previous life, I was an attorney, and I did renewable energy contracting. So I guess that's why I gravitated to this one.
Thank you.
I'm Marcos Incapié. I'm studying here at Natsuo Sustainable Development. I'm here because I worked in my country 18 years with energy transmission, high voltage energy transmission company. So I wanted to make like how you are developing these areas.
Hi, I'm Anand Gafni. I'm currently at the faculty of the Sustainable Development Program, but in the past, actually my PhD was in distributed simulation, so these things are quite maybe evolved out of what I did many years ago. But of course, areas of sustainability, in particular energy and transportation, are very interesting.
I am Gabriel, and I'm a master student in mathematics, but Khan is my supervisor. And my work is about environment models and energy models.
My name is Rami Awani. I'm the Director for Engineering and Advanced Technology at the Ministry of Innovation, Science and Technology. And I'm responsible to coordinate the cooperation with IIASA. And also we're interested in advancing all these researches, which I think are very important for the future.
Okay, any thoughts from what you all saw? You know, this is, I think it's really interesting because see many people in different, working from different angles on very similar questions. And I think on one end, the tools that are in IIASA already could use some of this, and also, and we always say that in meetings that we can also contribute, adding new layers to those models. So it goes both ways, either to use what's existing and apply it with what we do, or actually help to develop something that is even more advanced under those submodels as we do in the transportation or other. So Paul or any others?
Yeah, so just a bit of reflection on what we saw. So I think like I gave you the sales pitch I was obliged to give, right? But my personal feeling is that there's a lot of siloing in modeling and research, right? So it's always, and this is what we're taught, I guess, as academics, is to brag about what we do, right? And so it's very good for a variety of people to line up and say, well, we simulate renewable energy and we model renewable energy and so on. And you have to sort of get that out of the way first before you can have a conversation about, okay, but what are the aspects or phenomena related to renewable energy that your model does very well? And what are the ones that you're conscious that it does poorly, right? And once everybody is willing to sort of trust one another and let their guard down like that, then you can have very interesting, I find, conversations about where the methodologies will complement one another and where there are fruitful connections and collaboration. So I always really like having those kinds of conversations. I was at MIT for grad school. I worked in this global change program. So I worked with the FSCG model, and I had colleagues who worked on models of the power sector. And I took a class with Moshe Ben Akiva, so I know some stuff about the agent-based modeling. Definitely did not get involved with much of that. But yeah, so it's very clear that there are very strong intellectual traditions in these different areas, and there are strengths. So there are many things that are captured, for instance, in this sort of, I don't know if it's related to sim mobility or these other sort of frameworks that could never be put into message, and it would be very stupid and a waste of energy to try to put those into message, right? So I think, as you were saying about oligopolistic competition or other aspects of industrial organization, these are genuinely important, right? They can be substantial or fatal barriers to the development of new, energy technology industries and deployments. But it's very hard or impossible to include them in a model like message or our linked CG model macro, which is very rudimentary. So I think what that suggests to me is that if there is a growing collaboration between different Israeli researchers and IIASA, that would be a very fruitful topic or theme to pick up and to keep carrying forward, which is what sort of insights, and it may not be a direct hard linkage of one model to another or data feeding from one thing into another thing, but rather what are the stylized facts, right? What are the qualitative insights that we get that this cannot go beyond a certain level, right? So if we, for instance, from your work, found that the message model was producing more than 85% solar in Israel, we would say, well, message is obviously lacking something that is better reflected in that more detailed model, and we ought to at least put in a constraint or something like that. Otherwise, the picture out of the message model is not going to have fidelity to the work that you've done, and likewise for all the other teams, right? So I think those are at least from our point of view, in terms of we're aware, as I said during my presentation, that there's a lot of areas where we haven't been able to check the very fine-grained results and see if they pass a laugh test. So to have those eyes and to receive those feedbacks is super valuable to us, and would be very welcome from not just transport sector, but anything related to energy and climate. Yeah. So,
anyone else has thoughts? Lior, you had some thoughts before you?
Well, I think that's it. But then I'll tell you. You kind of ask what are the added value of such elaborations of industrial organization. The current model we're using at the Bank of Israel is a model in which we have elaborated on market structure and industrial organization. We have results from under the assumption of free markets and under the assumption of monopolistic competition, which is a little bit different. It's not oligopolistic competition, but it's a more sophisticated market structure. Now, there are two reasons to consider market structures. First, these models try to, in some way, to accord with reality, to reflect something which is more realistic, and the interaction between players in these monopolistic competition models are stronger. The elasticities, the price elasticities, income elasticities are a little bit stronger, which means that that policy has stronger influence on the results, and we can show it. We have some results on this issue. So this is basically its reality, and the fact that some markets do behave like monopolistic models and not free market models, and it has implication on the results. And this is the reason that it's important to consider.
Okay, last reflection I want to do is maybe about related to Moshe work about, on one end, the granulated, like more GIS, how much in the message or in other models, there is a way to do the more regional and the more specific, and also about the type of scenarios that they look at versus.
So I was just gonna follow up by email, but for instance, we had, as part of our Young Scientist Summer Program, we had a student who came, I think he was studying in Ireland, but he was from India, I'm not sure, but is now with us full time, and his YSSP project was about the global potential for rooftop solar. So they basically did some very sophisticated GIS work and image recognition to identify rooftops and quantify what is the area available for rooftop solar.
I think in Israel they did it already a few years ago. There's a work of I don't remember his name. That it tried to figure out what is the potential of PV over the roof.
And you also mentioned a figure that you had gotten from other colleagues in the government, right?
Yep.
Yeah.
The Ministry of Protection.
So, but to me, this is a classic example where because we start from the global perspective, we had this student who was trying to do this on a global scale. And I'm sure he did not go into every country and look for specific projections for those countries and say, does my global assessment line up very well? I'm sure he did some kind of validation, but probably not in that level of detail. So I think if you were to speak to one another, he would say, well, here are what my results say if we draw the boundary of Israel. And then you might have a very interesting discussion about why his numbers are not the same as the numbers that you are already seeing, right? So that, I think that's one example. And as mentioned, we also have had a stream of collaborators we don't have power sector energy system modelers in-house. So like an electricity system, right? The electric power system modelers in-house, but we've had a stream of students and collaborators who have tried to make linkages, for instance, between a European open source electricity transmission and distribution model and Message Europe, right? So those sorts of experiences, I think, would also be interesting to apply in this country.
Okay, so we're gonna end this session and go back to room 201, so 201, and we will do a short summary there of all of the panels. And I think we have quite a lot of things to follow up, and a few of the things that you mentioned, I will mention again in the summary. And I think also this edits group, which I also just recently joined this summer, I think could fit a lot of the demand side and social sciences people which are don't necessarily see themselves as part of it, and they're very much part of it. So great, thank you so much.
Thank you.
Thank you.